and it's all yours.
Thank you. First of all, let me thank the organizers for giving me the opportunity to speak in this series of seminars. Today, I will talk about this paper, EFT Strings and Emergence, that I published with to my supervisor, Fernando Marchesano. Oh, I cannot change the slide. Okay, now I can. The outline of the talk will be the following. So I will start introducing the two basic ingredients of the paper, so the emergence proposal and EFT strings. Then I will also introduce quantity related to EFT strings, which is the scaling weight, which allows to classify different infinite distance limits. Then I will describe the setup in which we are working, which is type 2A string theory compactified on a Claviao threefold. And I will start by showing how emergence works in a simple example. Then I will switch to a more complicated case, which is what we call emergent EFT string limits, which I will introduce later on. And finally, I will draw some conclusions. So the emergence proposal. I would like to start from the swampland distance conjecture. This conjecture states that in any effective field theory compatible with quantum gravity, each time that we go to infinite geodesic distance in moduli space, we encounter an infinite tower of states which is becoming light, and it does so exponentially with the field distance. The emergence proposal kind of reverses the logic of this conjecture. The emergence proposal says that it's precisely because of this infinite tower that is becoming light that we have integrated out from our effective theory that we encounter the infinite distance singularity. So more precisely, the kinetic terms that we see in our infrared theory emerge from integrating out these towers of states. And so, as I said, the infinite distance as well as the small gauge coupling limit, which we also usually encounter along infinite distance limits, arise from integrating out the infinite towers that are predicted by the swampland distance conjecture. So we will focus on the gauge kinetic functions in four-dimensional effective theories. And the idea is that we have a UV contribution to the gauge kinetic function defined at some UV scale, which for us will be the species scale and the species. And then this gauge kinetic function receives some one loop contributions, one loop corrections from these towers that are becoming light. And these corrections are the divergent part, which give the behavior that we observe in the effective theory, in the low energy theory. When we compute these corrections, we have to sum over a number of states, and these states are the number of states is the number of species, and they are all the states whose mass lies below the species scale. So we have to sum over all the states up to the species scale, which is our UV cutoff. And the species scale is defined in this way. So let me now go to EFT strings. So consider a four-dimensional effective field theory coupled to gravity, and let us focus on an asymptotic region of the moduli space where we have a perturbative axionic shift symmetry for some axions AI. In this region of the moduli space, an EFT string is a fundamental object, which means that it cannot be resolved in a four-dimensional effective field theory approach. It's an axionic string. So this means that when we go around the core of the string, the axions AI get shifted by some integer constants, EI, which are the string charges. And finally, when we approach the core of the string, which, as we will see, is an infinite distance limit in moduli space, all the non-perturbative effects that break the shift symmetry, the axionic shift symmetry, are exponentially suppressed, so the symmetry becomes more and more exact. These objects, the EFT strings, have a back reaction on the moduli. In particular, so as I said, there's the axion monodromy around the string core. The axions are shifted by some integer constants, and the back reaction on these axions drives them to infinity when we approach the string core. And we can parameterize this flow, which we call EFT string flow of the saxions in this way. So they scale proportionally to the EFT string charges, EI, and with this parameter phi, which is going to infinity. Along these limits, the tension of the string is decreasing monotonically and the string becomes asymptotically tensionless. So this means that the oscillation modes of the string are becoming massless. So they are a candidate as a tower, which is becoming light in this limit. But there can be additional towers, in particular lighter towers, which become massless with a faster rate. And this is captured by the integral scaling conjecture formulated in this paper, which says that in an asymptotic limit specified by an EFT string flow, the leading tower, which means the lightest tower, has a characteristic mass m star, which in Planck units scales as the EFT string tension to some positive integer power, W. And this W is our, what we call scaling weight, what they call scaling weight, and it can assume values 1, 2, and 3. Our goal is to test the emergence proposal along EFT string limits. And the setup in which we work is type 2A string theory compactified on a Calabi-Yau threefold, and we focus on vector multiplet moduli space. In this context, the EFT strings are NS5 branes wrapping the NF divisors in Calabi-Yau. We have some complex scalar fields with a real part, which are our axions, and the imaginary part are the saxions. And these correspond to the complexified Kähler moduli. And then we have some U1 gauge fields, namely the graviphoton, which comes from the Ramon-Ramon 1 form, and then some other U1s which come from the Ramon-Ramon 3 form. And we, as I said, we focus on the gauge kinetic function for these U1 gauge fields, which assumes this form. In particular, we focus on we work in a basis where the off-diagonal terms are vanishing. So we just compute the diagonal terms of the kinetic matrix. So in this context, the saxions are the Kähler moduli. So we consider these kinds of limits where phi is going to infinity, and these are large volume and strong 10 decoupling limits. So one can classify these infinite distance limits in terms of the scaling weight W, or equivalently in terms of the singularity index N, which is captured in the leading term of the Kähler potential. Of the effective theory, and one can try to reproduce the gauge kinetic terms via the emergence proposal, so computing these one loop corrections for the relevant towers along each limit. This classification of limit in terms of W in our context can be translated into a classification in terms of this quantity K and Ka, where K and Ka and KAB are contractions of the triple intersection numbers of the Calabi-Yau with the string charges. And this classification can also be formulated in terms of other languages used in the literature. For example, in this paper, they classify, they call them singularity types 4, 3, and 2 in terms of mixed Hodge structure. And in this other paper, W equals 3 would correspond to a large volume M theory limit, while W equals 1 and 2 would correspond to J class A and J class B limits. So in this table, I summarize some results for some components that have been found studying emergence in type 2 compactifications. And as we see, for W equals 3, the emergence proposal reproduces the scalings that we see in the effective theory. While for W equals 2, we have a mismatch of some components. So I will revisit this computation and see how this mismatch can be solved. And in W equals 1, also the correct scalings were recovered, but as we will see, these W equals 1 limits contain emergent string limits in the sense of the emergent string conjecture. And in this class of limits, we have an emergent critical string, and so the string modes dominate the light spectrum. So we will revisit this computation also taking into account the string tower. While for W equals 2 and 3, the leading tower is a KK-like tower. And so it's not a critical string tower. Okay, so the relevant towers, the relevant mass scales along these limits are reported in this table according to the scaling weight of each limit. So we have the Kaluza-Klein scale, which always has the same scaling, the lightest Kaluza-Klein scale, as well as the square root of the tension of the string, always goes like 5 to the minus 1/2. Then we have the mass of the D0 particles here, and the mass of the lightest D2 particle, which is given by a D2 brane wrapping some 2 cycle of the Calabi-Yau. And finally, here we have the species scale, but this species scale is computed by taking into account only the lightest tower, which is the tower of D0s. And in particular, as we will see in these two cases in red here, this computation will have to be corrected. Things do not work with this computation, but it will be corrected. So as I said, the lightest tower of states is given by D0 branes, but there's also another tower which is given by a D2 brane with some fixed D2 charges, and a generic world volume flux, which gives an arbitrary D0 charge. So this is a tower of D2 D0 bound states, and this is charged under the other U1s, which are not the graviphoton, and so this enters the correction to the gauge kinetic function. As I was saying, these two cases will need to be corrected, and the key point is that in order to compute the species scale correctly, we have to take into account all the leading towers along a certain limit, and not just the lightest one, where all the leading towers mean all the ones that lie below the species scale, parametrically below the species scale. So let me show how things work with a simple example. This is our Calabi-Yau threefold. It's an elliptic fibration over a P2 base, and we have two Kähler moduli, and these are the triple intersection numbers. So we have two elementary limits. We can send T1 to infinity or T2 to infinity. The first one is a W equals 3, and the other one is a W equals 2. And these are the scalings that we observe in the two limits by looking at the effective theory. And so one can try to reproduce them through the emergence proposal. And in this paper, these two towers of massless PPS states have been identified. And in particular, these charges are the D2 charges, and they are fixed, while we have growing D0 charge parameterized by this integer k. And if one tries to run the emergence computation with these two towers, we see that for the W equals 3 limits, we recover the scalings of the effective theory. There's a match between the two. But for the W equals 2, we have this mismatch for the 1-1 component. And so let us see how to solve this. The key observation is that while in the first case, W equals 3, the D0 is the mass of the D0s is the only mass which is parametrically below the species scale. In the second limit, we have two mass scales which are parametrically below. And so we have to consider a double tower of states instead of a fixed D2 charge and growing D0 charge. We should consider a double tower or a two-dimensional lattice of states where both the D2 and D0 charge are arbitrary. And this corresponds to a D2 wrapping the elliptic fiber of the Calabi-Yau plus generic world volume flux, which gives the D0 charge. So by taking into account this double tower, the species scale computation is corrected. Now we have two contributions to the number of species. And now we see that the species scale is lowered to the string scale, as it is in the W equals 3 case. And there are no other towers below parametrically below the species scale. So the only ones that lie below are the D0s and the D2s. So as I said, considering this double tower lowers the species scale and changes the number of species. So in principle, by lowering the species scale, we have less states that lie below the species scale. But what happens in the one loop computation is that there is a compensating effect, because now we are summing over a double tower, not anymore a single tower. So we have to sum over both k and j. And then for the 0,0 component, there's this compensating effect, and we recover the phi squared scaling as it was before. But now for the 1,1 component, we have the same computation, just with j and k exchanged. I mean, j squared instead of k squared here. And so we also get a phi squared scaling for the 1,1 component, which is exactly what we see in the effective theory. So now the emergence computation reproduces the correct scalings we see in the effective theory. And a general lesson that we learn from this is that this compensating effect, in order to occur, needs the leading tower in the species scale computation to enter the one loop correction. In particular, if there was another tower, multidimensional tower maybe, which dominates the species scale computation but doesn't enter these corrections because it's not charged under the U1s, this compensating effect would not occur. Okay, so this was for a particular example, but using the properties of the elliptic fibration, one can generalize this argument to more general double equals 2 limits of the class we are considering here. Let me now go to the double equals 1 case. In this case, the Calabi-Yau has a K3 or T4 fibration over a P1 base, and the NS5 brane is wrapping the fiber to give the EFT string. And in these limits, we have many leading towers, because all these towers lie at the same scale as the string scale. So among these towers, there's also the one of string oscillations. And so in principle, the computation of the species scale should include all of these towers. But in practice, we can focus on the leading contribution in the denominator here. And this depends on whether the EFT string is critical or not. If the EFT string is critical, then the string modes dominate the light spectrum and they effectively set the species scale. Otherwise, if the string is non-critical, then it has the oscillation modes are just a finite number of states, and the spectrum is dominated by bound states of D4, D2, and D0s. So we will see how the emergence computation works in both cases. And let me start by the non-critical case. So as I said, in this case, the dominant contribution is given by bound states of DP branes. And the spectrum of these charges takes this form. And the dimension of this lattice of charges is set by the rank of this matrix, which is, as before, this is the contraction of the triple intersection numbers with the string charges. So the rank of this matrix sets the dimension R of this lattice of charges. And we can compute similarly to, as we did before, the species scale with this multi-dimensional tower. And we see that the precise scaling of the species scale and of the number of species depends on this R. But once we go to the one loop computation, again, we have to sum over all the charges, all the components of the charge vector. And once we do that, the result is actually independent on this R, on the dimension of this tower. And we get the phi scaling, which is the result we wanted. And now I will switch to the critical case. In this case, the string oscillation modes are the ones that dominate the spectrum, and that set the species scale. So for the critical string, we have a mass spectrum of this type. The mass squared is proportional to the tension and the oscillator number n, and we cut off the spectrum when the mass is equal to the species scale, and we have to take an ansatz for the general. Sorry, is there a question? Oh, okay. We have to take an ansatz for the degeneracy of the string spectrum. In particular, we take an exponential degeneracy with this alpha, a positive parameter, and times a power law. And once we plug this into the species scale definition, we get these scalings. So the scaling of Nmax and the number of species is not so important for the details are not so important, but let me stress that the species scale now is given by the string scale, which goes like 5 to the -1/2 times some log correction. So it's slightly above the species scale, string scale, sorry, but just by some log term. And now we need to take an ansatz for the charge spectrum of the string modes in order to compute the one loop corrections. So at each mass level, n, we take to have some number of states as a function of the charges, Fn of q. And the spectrum of the charges once again takes this form as in the DP brane particles case. And this form of the spectrum is motivated by an argument based on anomaly inflow in the presence of axionic strings. So in particular, this argument follows the one outlined in this paper, but we generalized it to our n equals 2 supersymmetric context. And we found this type of spectrum for the string modes. And then this Fn of q, we take it to be non-vanishing only up to some maximal charge for each level n. And this maximal charge is such that its modulus squared goes like n. So the shadowed region here is the populated region in the spectrum, where the line saturates the BPS bound. And finally, these charged states, the spectrum of the string oscillations should be populated by charged states. This, as I was saying before, we need at least a significant fraction of the spectrum to be charged under the U1s in order for these states to enter the one loop computation and to give the corrections to the gauge kinetic function. Oh, and also we need to take into account this refinement of the one loop corrections. So in the corrections, there was this log term appearing, but actually in this paper here, they pointed out that there's always a positive constant here inside the log. And in this particular class of limits, it's important to take into account this constant. Otherwise, this would kill the leading contribution. And the emergence proposal wouldn't reproduce the correct scaling, but once one takes this into account, it gives the correct result. So now we are ready to compute the one loop corrections by plugging all our assumptions in this sum in the computation of the correction, and we see that we get again the scaling with phi as we wanted. And in particular, we get that independently of alpha and gamma of these two parameters in the degeneracy of the spectrum. So let me make some remarks. So we saw that the precise scaling of the species scale and of the number of species is not very important. What is important is that we sum over all the relevant towers along each limit. So all the towers that lie parametrically below the species scale. And it's also important that the tower or the towers that set the species scale also enter the one loop corrections. And in the double equals 1 limits, we recover the correct scaling through the emergence proposal for both critical and non-critical EFT strings. One caveat about this is that we did not compute the corrections to the moduli space metric, so it would be interesting to test that as well. One expects things to work whenever the spectrum is dominated by BPS states because of n equals 2 supersymmetry, which relates the moduli space metric to the gauge kinetic term. But it would be interesting to check that and to see if this poses further constraints on the distribution of states with the charges in the string spectrum. And now let me conclude. So we have seen that EFT strings are a useful tool to explore infinite distance limits of four-dimensional effective theories coupled to gravity. They allow to classify these limits, in particular using the scaling weight, which contains information about the leading, the mass of the leading tower, the lightest tower and star. The EFT strings in our context of type 2A compactifications are given by NS5 brains wrapping NF divisors. And in addition to the string tower, the other relevant towers are bound states of DP brains, wrapping internal cycles. And we tested the emergence proposal in this context, in particular in the vector multiplet moduli space and focusing on the gauge kinetic function. We've seen that in the W=2 limits, the relevant tower is a two-dimensional lattice of D2, D0 bound states. And in general, we need that the tower that the leading tower setting the species scale is also the tower entering the one loop corrections in order to have this compensating effect I was mentioning. And finally, in W=1 limits, which contain emergent EFT string limits, the oscillations of the critical string dominate the light spectrum. And so one has to assume that they are charged under the U1s. Of course, it would be important to look at explicit EFT string spectra and test our assumptions and see if they are satisfied. Thank you for your attention.
Thank you. Let's all thank Luca for the very nice talk with our club emojis. Thank you. I enjoyed the talk very much. We have time for questions. You can either raise your hand or just unmute yourself if you want to ask something. Otherwise, yeah, while people think their questions, I will ask something. So yeah, look, I think that this emergence proposal is certainly very interesting, and it deserves further work. So this was very interesting. So in your mind, you have probably looked at a lot of many examples. So like if, for example, trying to go beyond the particular setup that you used, or thinking about corrections to your setup, or in your mind, and from your experience, what is you think is the main challenge for the emergence proposal? Like trying to be the devil's advocate. Like you have this was evidence in favor, right? But like against or main challenge, what do you think?
Well, for maybe the first thing that comes to mind is that we looked at the scale, just the scaling of the leading term in terms of this phi of each quantity. So it would be interesting to try to do the computation more precisely and computing all the factors, and I mean going beyond just the scaling of the leading behavior. And well, as regards our work, as I said, we just looked at the gauge kinetic function. So it would also be interesting to look at the moduli space metric corrections and see if it works in that case for that quantity as well. Yeah, these are the first things that come to mind.
Right. Yeah, I was curious, like if you know of some other particular example, like maybe that you're not sure if like the things you found apply. No, like you said, some characteristic, like the tower has to play a role when you compute the species scale. In the case that is a charged tower, so I was just curious if there was some example elsewhere in the literature that maybe you guys thought, okay, I'm not sure about this one. Okay, well.
No, yeah. Now at the moment, I cannot. I wouldn't know an example where we are not sure if it works or not.
Right. Yeah, thanks a lot. Yeah. Yeah, if there's any other question. Okay. Let me check the chat or participant. Okay. Yeah. So if there are no more questions, we can stop here. Yeah, we are already over time also. So let me stop the recording.